excited for the potential of life elsewhere in our solar system?
Well, so are we.
Enceladus, one of Saturn's many moons, is by far the most promising body in our solar system. It has a unique chemistry, internal heating, and a global ocean.
We plan to send a mission to Enceladus to search for signs of life. Traditionally, a mission like this would be funded by the government, but we plan to use crowdsourcing.
And that's where you come in.
There are multiple stakeholders that might have a vested interest in our system. Scientists, who will obviously want the scientific data that we gather at Enceladus. Launch vehicle providers. We don't want to make our own rocket, so our system needs to fit on some commercially available system today. Mission operators. These are the people that will be controlling the craft once it arrives at Saturn. Our system needs to provide attitude and thruster control throughout its project lifetime. Manufacturers. We want to make the job easy on manufacturers, so we will only be using flight-tested material and no novel manufacturing processes. Regulators. It's no use if we go all the way to Saturn only to kill any life that's there, so we need to follow planetary protection guidelines. And you. We need to be able to provide our system to you for the cost that we say that we will. So from the previously discussed needs of the stakeholder, a list of requirements were made, and these are some of our more key requirements. First, the system must cost less than $500 million, not including the launch vehicle cost. That's based on NASA's Discovery class missions. Second, it must have a lifetime of 1 year in Saturn's orbit. That should give it ample time to collect data from Enceladus. Third, it must be able to provide attitude and thruster control for up to 3 weeks after data collection ends. And the reason that we developed this requirement is so we can satisfy planetary protection. Once data collection ends and the mission is over, we need some way to dispose of this so we don't crash into a moon of Saturn. So that 3-week period should give us the time to do that. In addition, our system must withstand accelerations of up to 5 Gs. That's so it can survive launch from Earth.
Now moving on to risk assessment and the stuff we might encounter while designing and developing our mission is firstly, lack of funding. Now we sincerely hope that you love our mission in order to back us, but in the unlikely event that we do not reach our funding goal, we will move to meet with private institutions as well as government institutions in order to meet our goal. So that risk can easily be negotiated. Now the second risk that we might run into is that our spacecraft is too big and might not meet the payload specifications of a current launch system. Now this can easily be mitigated by planning in advance and designing our spacecraft in such a way that it meets the payload specifications of current space launch systems. Now moving on to the third risk that we might run into is that of over budget and running out of money. Now this, again, can easily be negotiated by planning in advance and using technologies that have been tried and tested and have always fitted the budget of all missions. Now moving on to the fourth risk that we might run into is that of data acquisition issues as well as communication issues with our spacecraft. Now in order to mitigate such risks, we hope to work with companies that have provided technology for previous spacecraft missions that have always worked, so thereby reducing our chances of any failure during our mission. And now moving on to our fifth risk is that of a launch system failure. Now we hope to work with companies that have a reliable past and have always succeeded in launching spacecrafts onto their missions. And moving on to the final risk is that of space debris impacting our spacecraft. Now, although our mission is highly controlled and we make controlled orbits and maneuvers across the Saturn system in order to get into Enceladus, we cannot account for any space debris impacting our spacecraft and thereby causing our mission to fail. With that, I move on to concept generation.
So in our research of launch vehicles, we identified 3 potential launch vehicles for our system: the Delta IV Heavy, the Atlas V, and the Falcon 9. Now in calculating an approximate mass for our system and examining past outer solar system missions, we realized that a system like the Delta IV Heavy would be unnecessary for our applications. And between the Atlas V and Falcon 9, which have relatively comparable performance, we chose the Atlas V for its superior historical reliability.
So talking about power source, we did a lot of research as to what can power our spacecraft, and we came down to two of them. One is solar panels, and the other is nuclear power. Now, based on the previous deep space missions that we researched, we found that it was nuclear power that was generally used. But in the case of the Juno mission, which was a spacecraft that was sent by NASA to Jupiter, it used solar powers. Now, researching that, we realized that NASA said that they were pushing the use of solar panels to its absolute limit when they sent Juno with solar panels. And so we realized that in order to go to Enceladus, which is way beyond Jupiter, it would be an easy decision to go and use nuclear power as a power source.
So in researching operators, we identified 3 potential operators for our system. And these are people that will perform the day-to-day controls of our system after it's been launched en route to Enceladus, and then once it reaches Enceladus. So we have NASA, we have a NASA-affiliated contractor, and we have ourselves. So we wanted to remove ourselves from this equation because we wanted to focus primarily on the design of the system itself. So that leaves NASA and then contractors that are affiliated with NASA. Currently, contractors already manage a lot of day-to-day operations at NASA, and we see no real reason to buck this trend. These contractors are competent, otherwise they would not be working for NASA at the moment. So we believe that contractors are the best choice to operate our system day to day.
So now to discuss the need for operator oversight for this mission. There are 2 possible options that we've came up with. Either a constant supervision, where someone's monitoring the probe at every orbital maneuver and data entry, or we program it to be autonomous. Our decision came down to 2 different aspects: cost savings and technical difficulties. First, cost savings, we'd have to pay someone to be monitoring it at every step, whereas autonomous, it would just kind of do it. But at the same time, there's also a cost of programming. So technical difficulties come to, once at Enceladus, it'll take 68 to 84 minutes for communication to reach one way. So if we command the probe to do something, it would take 68 to 84 minutes to get there, and not much time to get back for us to know whether it's successful or not. And because of that, we have decided to go with autonomous.
So we have several options for how our spacecraft will examine Enceladus. We can use a lander, which is subject to a lot of regulations through the Planetary Protection Code, so we don't want to deal with that. We could go for an orbit of Enceladus, but unfortunately most orbits of Enceladus are unstable due to its very small size, so we're not going to do that. Which leads us to a flyby, which means that we would orbit Saturn. So we have 2 options for thrust: ion thrusters or chemical systems. We will be in orbit around Saturn, and we'll need to reach Enceladus through various orbital maneuvers. Ion thrusters, while much more efficient, unfortunately are slower, and so because we will need a lot of very precise and very fast burns, we've chosen chemical systems.
Finally, for our concept generation is instrumentation. Now, we have narrowed it down to these 2 options because of mission critical goals, which is to analyze particles that are spewed into space from Enceladus through its vents. First off, we have the mass spectrometer. This will be analyzing all the gas particles that are being spewed into space, and this is actually similar to previous research done. The big change is the Enceladus ICJet analyzer. This is a similar device, but has been optimized for particles between the range of 0.1 and 100 micrometers. These 2 combined, we believe, will help us decide whether if there is truly life on Enceladus or not.
So now, moving on to our final mission design, we started off by blasting off of Earth using an Atlas V rocket, and once in orbit, we used the third stage to thrust us towards Saturn.
Now, once our system arrives at Saturn, it'll use some of the larger outer moons of Saturn to slow down and go on somewhat a tour of the moons as it gets closer and closer to this inward orbit of Saturn, which will allow it to orbit Enceladus multiple times during its lifetime.
And so while it's in orbit around Saturn, flying past Enceladus, it will be able to transmit data back to Earth, where it can be analyzed by scientists.
Now, once the lifetime of this mission has concluded, of at least 1 year, we will have enough delta V left in the probe in order to safely deorbit into Saturn's atmosphere, effectively destroying the probe but adhering to the planetary regulations.
So that concludes the scope of our design analysis.
So, what all did we learn from this project?
It's a good question.
Well, we learned that risk assessment was actually a very important part of our design process. We learned that if we thought about our risks earlier on and we planned for them, it would increase the risk, it would increase the success of our mission.
We also learned that staying solution neutral during requirement generation is very difficult. It becomes very easy as you're making requirements to start thinking of the solution and not affecting the rest of the requirements that you generate.
We also learned that tools like functional analysis are very useful, especially in concept generation. Functional analysis made us go through and develop a list of functions that our system needs to perform in order to perform successfully. And then for each of these functions, we could go through and ask the question, what are different concepts that will allow us to perform this function successfully?
Finally, prioritizing needs was very helpful later on when we were trying to make design decisions for what we wanted to use for each component of this design process. Knowing what need was the most important that it be met really helped that later on.